Welcome to today's AM Academy webinar, part of our ongoing series designed to make cutting-edge materials science and engineering knowledge more accessible. My name is Zara and I'll be your host for this session. And today's talk is on advancing aromatic bromination via the use of flow chemistry for modern synthesis, hosted in collaboration with one of our AMLearn users at the University of Liverpool. I'm very pleased to introduce George Lyall-Brookes, who is a doctoral researcher. And in this session, George will explore how a traditional batch aromatic bromination process was translated into continuous flow, enabling access to expanded reaction conditions and chemical space, the use of algorithmic optimization to efficiently identify high-yielding reaction conditions using AMLearn, the development of both heat-activated and UV-activated bromination pathways without catalysts or strong acids, mechanistic and kinetic insights that clarify the underlying reaction pathway, and the application of the developed method across a broader range of aromatic substrates to demonstrate the versatility of the procedure. We'll also leave some time at the end for a Q&A, so feel free to drop your questions into the Q&A box throughout the session. And with that, I'll hand over to George to begin.
Perfect, and thank you for that introduction. And yeah, as was said, I'll be talking over our recent work on the development of a aromatic bromination procedure in flow. Just to start off, for those not familiar with bromination chemistry, I'll give a quick overview. So firstly, here is it's a figure taken from an excellent and comprehensive review on the use of bromine and bromo-organic compounds in wider chemistry. So as you can see here, there's sort of a plethora of applications, and it's particularly prevalent in organic chemistry. So to generate these bromo-organic compounds requires the use of brominating agents. So the most simple of these brominating agents is molecular bromine. So this is in liquid form, and it is a particularly potent brominating agent. However, with this potency comes a lack of selectivity, so it's hard to control where you will brominate on the compound. And also with that potency comes sort of safety risks coming in the form of toxicity. So as such, a lot of work has been conducted on the development of solid-based brominating agents. And the most popular of these, arguably, is bromoxycinamides, which can be seen here, otherwise known as MBS. So MBS is particularly popular due to the fact it is a commercial compound, so it is relatively cheap. It also enables a consistent low concentration of the bromine, which is great from both a safety perspective and from a selectivity perspective. There are downsides in terms of sort of downstream processing of the succinamide core, although on the whole it is a brominating agent that is often turned to for bromination reactions. And the reactions themselves can the most popular reactions can be sort of categorized into two categories. So benzylic bromination, which is typically achieved with MBS, and this proceeds via a radical pathway. And this was traditionally done with radical initiators. However, again, there was safety concerns there. So in recent times, benzylic bromination is primarily conducted via UV activation and photochemistry. And then the second class of bromination is electrophilic bromination. So here in the middle, you can see the electrophilic bromination of an alkene generating the dibrominated compounds. And then on the right here, electrophilic aromatic bromination. And aromatic bromination will be the topic of this talk today. So when conducting aromatic bromination, particularly with MBS, if you don't have a activated aromatic in the form of the presence of an electron donating group, you typically need to activate your brominating agent to facilitate the transformation. This can be done primarily through three methods that are outlined here on the screen. So the first of which being Lewis acid activation. So this works by coordinating with either one or both of the carbonyls on the NBS molecule, which then activates the bromine to attack from the aromatic ring to facilitate the transformation. Bronsted acid activation acts in a similar manner, but instead of a Lewis acid, here you have a proton source, which then coordinates with the carbonyl, again activating the bromine in the same manner. And then the final one operates in a slightly different manner, where a Lewis base forms a halogen bond with the bromine, which again activates the bromine for the transformation. So this is typically achieved either via strong acids for Bronsted acid catalysis activation, or that with the use of catalysts, whether that be Lewis acid or Lewis base, and both have advantages and drawbacks. So the use of strong acids is a particularly reactive procedure. So it's particularly useful if you're trying to brominate severely deactivated compounds with multiple electron withdrawing groups on the ring. It also this high reactivity also means that the reaction times can be very quick, which is also obviously advantageous from a throughput perspective. However, limitations. Due to the presence of these strong acids, it's unavoidable that the conditions are often very harsh. And as a result of this, you typically get poor selectivity. Similarly, how I was talking about with the molecular bromine, it's difficult to control where you brominate on a compound of interest. And then moving across to catalysts. So in direct contrast, you have typically very mild conditions, which is obviously advantageous from a safety perspective. And also in turn, that means you have improved selectivity where you can control where you brominate on the compound. However, these catalysts are typically very expensive. They're often not commercially available, and a lot of research groups have spent a lot of time and money on developing these catalysts that often require multi-step synthesis to generate the catalysts themselves even before the transformation commences, which can be prohibitive to conducting the transformation. And also, as a result of the sort of mild conditions, you can also have long reaction times where in batch reactions are often taking up to 24 hours for a desired transformation. However, one of the ways that you can negate these long reaction times is via integrating flow chemistry. So here on the screen, you can see a Vaportech flow reactor. So this is the E-series flow reactor from Vaportech that all of the work that I will talk about today was conducted on. So unlike in batch chemistry, where everything is done in glass round bottom flask typically, the reaction itself happens in tubes here in the reactor. So here is just a schematic representation of the same reactor, and I'll break down some of the key components of these systems. So first of all, and arguably most important for flow, is the pumps. And these deliver your reagents to the rest of the system. And here is where you can see the pumps on the Vaportech system. So these are peristaltic pumps, and they work via a central motor that's hidden underneath this plastic cover here, which compresses the some tubing that's inside that cover to force a liquid from the inlet to the outlet to deliver your reagents at your desired flow rate. This flow rate can influence the residence time that I'll speak about in just a moment, and you can also influence your reaction stoichiometry by altering the flow rates of the two pumps. Once you've got your two reagent streams pumping, you then require the mixing of the two streams, and this is achieved can be achieved via the use of a mixing piece. So the one here shown on the schematic is a Y-piece mixer, although these come in many different shapes and forms. So you can also get them in T shapes or more complex shapes, sort of heart-shaped mixing pieces have been reported in the literature previously, all with advantages and disadvantages again. So once your two reagent streams are mixed, they then enter a reactor. And as I was saying, these reactors consist of small, narrow diameter tubing. So in comparison with batch chemistry, you get improved heat and mass transfer, which is often favorable for your chemistries. Also in this Vaportec system here, it's contained within this glass housing where you can control the temperature via the software embedded in the reactor, and you can also monitor the temperature via the use of a thermocouple here. And then finally, we also have a back pressure regulator, or a BPR, which allows you to pressurize your whole system, which allows you to heat above the boiling point of your solvent system that would be typically able to achieve at standard pressure. So you can heat far in excess of these boiling points. So now I'll move on to sort of the existing bromination chemistry in the flow literature. So as I sort of alluded to previously, benzylic bromination is prevalent in flow due to the use of photochemistry and UV activation to carry out these transformations, as the light penetration is much greater in flow due to the narrow diameter of the tubing in comparison with batch, and you can also get a uniform path length, so that satisfies Beer-Lambert law as well, which is obviously preferable for carrying out these transformations. However, in comparison, aromatic bromination procedures are comparatively underrepresented, with only a few examples covered in the literature. I'll sort of list some of them now. So here, these first two examples either make use of molecular bromine or generate the bromine in situ in the second case from HBr and KBr. So although there is still a sort of hazard associated with this, in flow you can deal with these sort of hazardous reagents more easily, because you're only dealing in smaller volumes prior to quenching due to the reactor sizes. So a typical reactor coil will be somewhere around, especially on lab scale, up to sort of 10 mil. So you're never having more than 10 mil of unreacted material at once. So that's obviously a benefit from a safety perspective. And then this final example is the bromination of porphyrins, and is one of the only examples in the literature that uses MBS as a bromine source. So for this work, we sought to try and develop a aromatic bromination procedure in flow to sort of fill this gap in the literature, so we could generate the compounds efficiently and in a quick manner, so not requiring days of reaction time, and you could do it in a mere minutes. So to do this, we first looked through the literature for suitable batch procedures that we thought would be amenable to translation to flow. And of particular interest was this procedure reported by Baxter, that relied upon the use of a mandelic acid catalyst that can be seen here, which carried out a Lewis basic interaction with the MBS reagent that they used to activate it for the transformation. The solvent system they used was a acetonitrile water solvent system, and then this was done at room temperature. So why this was particularly advantageous, or we deemed it would be potentially advantageous, is the mandelic acid catalyst is both mild, so satisfying safety concerns, and is also relatively cheap, which is always good when developing a chemical process. The aqueous solvent system is particularly good from a sort of green perspective, so environmentally friendly. And they also, in the original publication, report a broad scope showing the wider utility of the procedure as well. However, some limitations, as with most aromatic bromination procedures in batch, long reaction times. So the reaction for most of the substrates reported in the paper required 24 hours of reaction time. And the procedure was also incompatible with strong Lewis basic substrates, which is obviously a limitation from a broader perspective. So to do this, we first sought to translate the procedure to flow. So to do this, we used an exemplar substrate from the original publication, which you can see here, so 4-methoxyacetophenone. And we just use a simple two feeds solution setup. So your two pumps here combined with the Y mixer again, 10 ml coil, and then your back pressure regulator and collection flask. So as you could probably tell by the phrasing of original procedure, where we had the 4-methoxyacetophenone in one solution and the MBS and mandelic acid in the other, this did not end up our original solution compositions, and this is why. So we conducted an initial stability screen where we, over a 15-minute residence time at a temperature of 50 degrees, we ran the reaction for 90 minutes, collecting a sample every 15 minutes and measuring the percentage conversion of each of these samples. So as you can see, conversion here started at 30%, and then by the final sample had reduced down to 21%. And the reasoning for that can be sort of inferred from these solutions here on the right of the screen. So this solution here on the right, the light golden color, is what the solutions look like upon preparation. And then just after 90 minutes of being made up, the solution transitions to this dark orange color, indicating that degradation or unwanted side reactions were occurring in the feed solutions prior to even entering the reactor. As such, we altered the composition of these feed solutions. So in solution 1, we had our 4-methoxyacetophenone species and mandelic acid, and then in solution 2, we had our MBS. And whilst conversion for this initial data point dropped by near 50, well, over 50%, we could achieve consistent results across the 5 samples collected, with the only variation being due to sort of experimental variation as opposed to any kind of degradation. And this was important to establish to ensure the reliability of our data points for optimization, which I will discuss in a moment. So, as I've mentioned a couple of times already through this talk, the aromatic bromination procedures in flow are very sparse. So, gauging what would be sensible conditions for this transformation would prove challenging if you were just going in hot and not doing any kind of screening first. So, we wanted to deem what the sort of sensible conditions were, or in other words, what the chemical space for the reaction was. So to do this, we first screened different residence times. So this screen was conducted at 50 degrees C with 1.2 equivalents of the MBS and 0.2 equivalents of the mandelic acid, which is comparable to the conditions in the original procedure outside of altering the temperature. And as can be seen here, a maximum conversion of 49% could be achieved at a residence time of 25 minutes, with a decrease to 46% when the residence time was further increased to 30%. Although we believe this is more than likely due to hardware restrictions, with the pumps operating at the low enough flow rates to achieve these resonance times other than outside of something intrinsic to the chemistry itself. We then screened temperature. So fixed the residence time here for this screen at 15 minutes, and once again used the same equivalents of the MBS and mandelic acid. And here there was sort of a proportional relationship observed, where conversion increased with temperature, with our maximum conversion of 61% achieved at a temperature of 125 degrees. So we then wanted to vary the concentration of our MBS and mandelic acid to see what effect this could have. And to do this, we used the optimal data point up to this point of the 15 minutes, 125 degrees at 0.2 equivalents and 1.2 equivalents of the acid and mandelic and MBS respectively. So as we've talked about already, that was returned a 61% conversion. So then when we removed all mandelic acid from the reaction, this conversion dropped by nearly 40%, yielding a 22% conversion. And then interestingly, when you had a one-to-one relationship of the acid and the MBS, this did very little to alter that conversion, with just a 4% increase to 26% conversion. And then upon a doubling of the MBS equivalence, we achieved the highest conversion to this point, so returning a 79% conversion when 2.4 equivalents of the MBS was used. And then finally, at some of the higher temperature reactions that we'd conducted so far, we started observing the formation of a dibrominated compound, which I'll show on the next slide, sorry. So we wanted to screen this to gauge at what sort of conditions this would form at. And you can see here the top conditions, so 15 minutes residence time at 130 degrees. With 0.3 and 2.14 acid and MBS, we got 29% of the dibrominated species. So this data could then be used to help guide our algorithmic optimization. So the 12 data points that we collected as part of that screen was compiled to form a training data set for then subsequent algorithmic optimization. What we deemed was the relevant chemical space was between 0 and 1.2 equivalents of the mandelic acid, 1.2 to 2.4 equivalents of the MBS, and then we screened across 25 to 130 degrees C, which was partly limited by hardware again and the operating temperatures of the flow reactor. And then residence times of 15 minutes to 30 minutes, which would again was limited by the hardware and the flow rates that the pumps could operate at, particularly at the upper end of that residence time range. So we then fed this training data set into AMLearn, which is the accelerated materials product, and embedded within AMLearn is the NEMO algorithm, which was developed and reported by the Lapkin Group at Cambridge. And this algorithm would suggest what it deemed was a high-yielding reactions based on the data it had been fed in. So we then went and manually carried out these reactions using our flow reactor, and then conducted offline NMR analysis to generate a percentage conversion for each of these reactions that could be then fed back into the algorithm in an iterative manner, generating the next set of experimental conditions to carry out. We carried out 5 of these algorithmic suggested reaction conditions. However, within just 2 reactions, we obtained what was deemed an optimal conversion of 94% of the monobrominated species with none of the dibrominated species observed. And this was conducted at a residence time of roughly 21 minutes, a temperature of 98 degrees, and then a MBS equivalent of 2.4. As you might have noticed, that reaction required none of the mandelic acid catalysts, so sort of counteracts what I was saying at the start with the different methods of activation for MBS. However, this does imply that reaction is instead being driven by high temperatures and not by some form of catalyst. So this led us to posit that potentially the reaction was being driven via a radical mechanism as opposed to a sort of the traditional electrophilic mechanism for bromination. So to investigate this, we used the optimized conditions that we have just discussed and did this in the presence of this compound here, tempo, which is a radical trap. So any bromine radicals that were, if they are being generated in the reaction, would be quenched by this radical trap. So when we carried out this reaction, we returned a 15% conversion of the brominated species, indicating that the reaction was, in fact, proceeding via a radical pathway, as it was significantly inhibited by nearly 80% when tempo was used. And then for further confirmation, we also conducted the reaction in the presence of this epoxide species, which acts as a acid trap, as we also wanted to make sure the reaction was not being catalyzed via the in situ generation of HBr and was in fact proceeding via the radical pathway. And as you can see here, by the 94% conversion, we confirm that it was in fact not being catalyzed by the acid in sort of a bronze acid catalyst kind of situation, and as it was unaffected by the presence of this epoxide species. As such, we thought that if the reaction is proceeding via a radical pathway, why can't we activate it via the UV instead of heat? So to investigate this, we once again use the Vaportec E-Series reactor equipped with the UV 150 photochemistry attachment. So this reactor works via the use of a mercury lamp here submerged into the reactor where your tubing is housed. You also have the same temperature control, and you can also attach external cooling to prevent any residual heat from the light source as well. So we didn't change our flow schematic, so the same solution compositions, and we used a 10 ml coil for this investigation. So excitingly, it did prove the case that we could catalyze or could activate this reaction with UV, and we obtained a 95% conversion in the same residence time of 21.39 minutes. And the use of UV also enables us to significantly lower the temperature of the reaction to 20 degrees C. And that also meant we could in turn reduce the pressure down from 5.5 bar to 2 bar. Interestingly, if we didn't control the temperature that was given off by the light source, we observed a significantly reduced conversion, and I'll talk about the potential reasonings for that slightly later in the talk. So given that we've now developed a optimized procedure for the full methoxyacetophenone species for UV activation and heat activation, we looked whether we could expand the scope of this procedure to include the Lewis basic substrates that the original procedure could not accommodate. So we primarily did this via the use of alcohols and amine groups. We also posited that the introduction of a stronger electron donating group in the form of the hydroxy and the amine group would lead to bromination at all orthoparasites available, excluding any ones that had other functionalities already present in there. And to investigate this, we carried out some initial screening on some hydroxy and amine containing species, using the optimized conditions that we'd previously developed for the heat activated procedure. But unfortunately, we observed poor solubility in a lot of these species, primarily due to a lot of organic compounds being particularly insoluble in the water. As such, we then conducted a solvent investigation, and seeing as the water was deemed the problem in this scenario, the obvious first attempt to alter the solvent system would be to conduct it into neat acetonitrile. However, this returned 0% conversion. So we then investigated various different ratios of the acetonitrile and water, and all of them returned very poor in comparison conversions of the brominated species. We then investigated whether we could substitute the water for another solvent, so in this case ethanol. So we tried both 50-50 acetonitrile ethanol and neat ethanol, and again both of these returned 0% conversion. And then finally we altered the method of activation to UV, and in the acetonitrile solvent system again. And whilst we did actually see some conversion to the desired product this time with 35% conversion obtained, it's still a significantly reduced conversion from the previously optimized conditions with a near 60% drop in conversion there. As such, we sort of came to a conclusion that the water must be pivotal to this reaction and driving the successful transformation. So we then probed whether altering the water in the solvent system for D2O would impact the reaction and whether we would see a kinetic isotope effect across both the heat activated and UV activated procedures. So as you can see here, when the D2O was introduced into the heat activated procedure, it had no impact on reaction success with a 94% conversion obtained in the previously optimized residence time. However, for the UV activated procedure, a significantly reduced yield of 57% was obtained when D2O was used. However, this could be increased to 78% upon an increase in residence time and then further increased to 93% with a further increase to residence time, indicating that the reaction was not inhibited, it was just that the rate was being slowed down. This led us to suggest that the reaction may in fact be sort of catalyzed or activated by in situ generation of a hydronium ion from the water in the solvent system, which could then mean the NBS and particularly the NBR bond in NBS was more susceptible to cleavage via either heat or UV, generating the succinimide radical and the bromine radical. And this was sort of the basis for this conclusion, as the formation of the hydronium ion is much faster than the formation of a D3O plus ion from D2O. It's also sort of explains a lot of the experimental results that I've talked about already today. So in particular, why when we carry out the reaction without the presence of water, we obtained 0% conversion with heat, although we still obtained some conversion of 34% when UV activation was used. And that is likely due to the fact that UV light is much better at cleaving that NBR bond than heat. So even in lieu of having the presence of the hydronium ion in the reaction mixture, you are still seeing some cleavage of the NBR bond, so you're still seeing some bromine radicals that can carry out this transformation. Similarly, it also explains why at higher temperatures we're observing more of the dibrominated species, as when hydronium ions are formed via heat under thermodynamic control. So the higher the temperature, the more of the H plus ions will be in solution, and also the more of the H3O plus ions will also be in the solution, which can then activate the NBS more readily, meaning the bromine can carry out more reactions, leading to the dibrominated species. And then finally, it also explains why when we don't control the temperature in the UV activated procedure and it can reach close to 40 degrees, we see a reduced conversion, and that is because the UV activation of the hydronium ion is under kinetic control. So when you increase the temperature, you just increase the termination events, meaning that there is less of a concentration of the hydronium ion in the solution, so less of the bromine radicals as a result. So then, armed with this additional process understanding, we then aim to expand our substrate scope to include the compounds that obviously were still soluble in this acetonitrile water solvent system, and we turned our attention to this species, so 4-hydroxybenzaldehyde, and everything that I've said so far, you would probably expect this dibrominated species to be the one that forms due to the increased electron donating properties of the hydroxy group, and that proved to be the case. However, we did want to see whether we could achieve monobromination, although unfortunately every attempt to do this proved unsuccessful. But as a result, we actually uncovered something interesting about the reaction as a whole. So at the previously optimized resonance time for the reaction of 21 minutes, we could obtain 64% isolated yield of this dibrominated species. However, if we reduced the resonance time to as little as 3 minutes, we could see a near 30% increase in the isolated yield, returning 96% of the dibrominated species, indicating that potentially, if you have a stronger electron donating group and the aromatic ring that you're trying to brominate is more electron rich, you may even be able to further reduce the resonance time down for the reaction down to 3 minutes. So to see if this held true with a broader range of substrates, we expanded this to more electron-rich or more electron-rich species. So you can see here that across the compounds, we have obtained good isolated yields at a resonance time of 3 minutes, and we can obtain dibromination or tribromination, depending on the positioning of the other substituents on the ring and their electron donating withdrawing properties. We could also selectively monobrominate compounds if they had a similarly weak electron donating group in the form of a methoxy group, similarly to the 4-methoxyacetophenone species. However, for the aldehyde species, we did also see dibromination and some starting material remaining at the end of the reaction, potentially meaning that more optimization on this specific substrate would be required if we wanted to increase that conversion. And all of these monobrominated species was obtained over a resonance time of 21 minutes, again due to the weaker electron donating properties of the methoxy group. Now expanding the scope further upon the bromination of the salicylic acid derivatives, it stands to reason that you would assume that these products on the right would form. However, as you can see here, that was not the case, and these were not the products that we observed. We instead observed a Hunsdiecker type reaction, so decarboxylated bromination. You can see where the carboxylic acid group has left and where the bromine has formed by these red bonds. So this reaction was initially conducted with the use of silver salts to enable the transformation, and then through development that transitioned to transition metals to catalyze the reaction, whereas obviously we have no either silver salts or transition metals in this procedure. We're not the first to report decarboxylated bromination. Many groups have done it, and the La Rosa group at Manchester have recently, or fairly recently, reported quite a comprehensive procedure for decarboxylated bromination. However, to the best of our knowledge, this is the first example of a decarboxylated bromination procedure in flow. And also, as all of the other procedures that have been reported thus far are in batch, they typically require long reaction times. So the procedure reported by the La Rosa group that I just mentioned required 16 hours of reaction time, whereas we can do it here in as little as 3.1 minutes. I just want to preface, this is only sort of initial preliminary data. Much more work would need to be done to investigate the potential selectivity of this procedure and also the mechanistic profile of this procedure, whether it was in fact like the other reactions proceeding via a radical mechanism. Having completed that, we then turned our attention to the UV activated procedure. So we screened a smaller subset of the molecules, and in general, we managed to obtain either comparable or better yields, with the exception of this isopropyl species. And also, we were still able to carry out the decarboxylated bromination procedure under UV activation. So with that said, all that's left is to thank the wider Slater group, in particular Anna, Firdaus, Alex, and Jazz, who helped with all this work, and then the CDT for Digital and Automated Materials Chemistry for funding me, which the logo you can see here in the top right, and then obviously the UKRI as well for funding that CDT. And then finally, thank you for your attention, and I'll be happy to take any questions. Thank you.
Again, thank you so much, George, for that insightful session, and thanks to everyone in the audience for joining us today. A quick reminder that this webinar is part of our ongoing AM Academy series, where we share knowledge and tools to help accelerate materials innovation. And you can explore more webinars, articles, and technical resources at acceleratedmaterials.co/AM Academy. And thanks again for spending your time with us. We really appreciate it. Have a great day, and we hope to see you at the next AM Academy session.
Thank you.